info. One, both the bonus quiz and the Kim and Life grades have been completed and posted to Canvas. I don't think there's a lot of questions with that. The next Kim and Life is due in December? I think December 1st. You know what? I'll report back to you on that on Wednesday when it becomes the recurring info at the end. So those are all done. You should see, I was sure it only helped your grade. I like triple checked 8 times just to make sure nothing terrible happened. But it did exactly as it should. So there's that. Mini exam 5 is 2 weeks from today. Try to keep us up to date. It's a new month. Important info. The last day to withdraw from any fall 2021 course is November 12th at 5 p.m. Withdrawals are basically a way, so if you are earning a D or an F, particularly an F in this course, you are not passing. You are welcome to talk to me, but I'm going to recommend that you withdraw more than likely. If you withdraw your transcript just as like a W, it basically means that you were like, and I'm out. I'm leaving this party. If you go on to complete this course and earn a D or an F, that is going to be on your transcript from now until eternity. There's no erase button. So UNF gives you the option of grade replacement, which means that when we calculate your final graduating GPA, we will use the higher of the 2 values. It doesn't mean that this semester goes away. It's still going to be there. To make it acceptable, I withdrew from a course in college. It was, I don't know, some really difficult math class that I'll be honest, I was failing. I did all the things. I went to class. I did my homework. It just went in one ear and out the other. Not to make you sound better, because I'm going to recommend that you retake this course. I never took it again, and I changed my minor and moved on with my life. So that is an acceptable choice. I have a job. I'm a regular professional. Most people, most college professors, more than likely withdrew from a course or earned unacceptable grades at some point in their career. It's not just me. So if you have questions, let me know. I'll be sending emails if you are not, if I am concerned about your ability to, if you're, well, I guess if you're failing. Like last week on Wednesday, my office hours are just going to be 1 to 2. I don't think there's anything else that's going to fall in that time slot. It's an urgent meeting, but I found out about it before the day before, so that will adjust, kind of like last week. They'll just be from 1 to 2. Questions about any of this info, Canvas questions, life questions?
So when you say withdrawal, can you still retake the course even if you do withdraw?
Yeah. So a withdrawal basically means that here are other ways why you might withdraw. If you were taking tennis and you broke your arm, you cannot, maybe you could still tennis, but it's not going to be the same. So maybe you took a withdrawal. Now that probably falls into like a medical withdrawal category, but a withdrawal basically gives you, when you apply to graduate school or professional school or anything post UNF, or if you want to leave UNF and go to any other institution, a withdrawal basically means that you did not complete the course. Most of us kind of, not assume, but there are a lot of reasons why you could withdraw. In this semester, you might have somehow enrolled for 25 credits. It's a terrible plan, don't do that. But you withdrawing from something just means that you didn't complete. There's no withdraw fail, withdraw pass. It just is a W. People call it different things at other institutions. I think at A&M, at one point, they were called Q drops. So we just called it the quit date, which in hindsight is not all that great. But you are welcome to retake the course. If you need it for your major, you can go on and continue to do that. There may or may not be financial aid implications, which are way outside of my purview, and I'm happy to connect you. If you have questions, I'm happy to answer those, either after class or privately in office hours. If you're like, can we talk about where I am and where I should be? But yes, we can do that. Oh, not a question. Any other questions, comments, concerns, choices, life updates? No. I forgot my dog's picture from her Bumblebee outfit, but she was not participating in her photo shoot yesterday, so she just looks like this. the whole time. Like I am murdering her by making her wear a cute costume. If your periodic table is not out, you might want to grab it. If your periodic table is out, that's super. Oh, so cute. Okay, so today, in the end of chapter 6, we are going to take all the topics that we've learned, because if you had to give chapter 6 a main point question, like what is it that we're learning? What we are learning is, where are the electrons? So far, we've said, okay, it's in the n equals 5, L equals 1, m sub L equals, m sub S equals. The reality is that that information is the same as saying, oh, it's in the 5p orbital. So what we're going to do today, and on Wednesday, because I don't think we'll finish, is to think about how do we take all this stuff that we know with quantum numbers and orbitals and apply that to the periodic table. 99.99% of elements have more than one electron. Just hydrogen has one. So everybody else has to have two. And so today we're really going to think about where are they, what do they do when they get there, and how can we write and draw that information so that if I ask you, give me that information, or I show you parts of it, you can start to tell me more about that. So we are going to talk about a couple of different things. We're going to talk about, so last time we ended with the Pauli exclusion principle. So the Pauli exclusion basically says no two electrons have the same quantum numbers, or the same 4 quantum numbers. So basically, any orbital contains 2 electrons. One has a plus 1/2 and one has a minus 1/2. And so, in addition to that, we also know that orbitals can hold up to 2 electrons. And so we tend to indicate that if we were to draw those as a line with the orbital underneath, and then 2 single barbed arrows. A single electron only has 1 wing on this arrow. If you put 2 wings, that indicates something else. And in order to indicate that they do not have the same 4 quantum numbers, we show that 1 goes up and 1 goes down. If you are feeling super positive, you can start with all ups. If you prefer down first, that is completely acceptable. I will always write mine this way, probably because I have some sort of compulsion, not a compulsion to do that, but that's just how I think about it. You do not have to think about it this way. I'm just going to show you that way. So Hund's rule tells us that we have degenerate orbitals. So if we think about our end states, we know that L equals 0, L equals 0, L equals 1. So in the n equals 2 state, we have the s orbital and the p orbital. And so the p orbital is composed of 3 unique and identical orbitals. So for 2p, it's composed of the 2px, 2py, and 2pz. these three orbitals are at the same energy. So we call them degenerate. Now, in today's world, degenerate is not I don't want to say it's not a kind word, but people don't use it as a descriptor in a positive fashion. When I say these orbitals are degenerate, all I mean is that they're all the same. They're at the exact same energy. So in this diagram, everything in the n equals 2 state is degenerate with one another. The reality is when we start to add more than one electron, what we start to see is what's called orbital splitting. Basically, they start to separate out a little bit. So we have the 1s orbital, then we have the 2s and the 2p, where the 2s is slightly below in energy, the s is below the p, but all three of the p orbitals are at the same level. So this applies to Hund's rule. When we add electrons into this, which is what we're going to do, we add into degenerate orbitals one electron at a time in the same spin. So we would add one here, one here, one here. And once we get all the way full, we're going to go back. Now, why do we do this? It is lower in energy. I think of orbital filling as riding a bus. I would like you to picture a yellow school bus. In my childhood, they had long bench seats, usually 2 humans to a bench seat. If you were the first kid that got picked up, you could sit anywhere you wanted, in the back, maybe on the right side. The next kid that came in can sit anywhere except for literally the spot where you are, right? Now, depending on how your bus ride worked, for the most part, everyone wants to sit alone. My friend called that the courtesy seat. You want to leave some space between you and the human you usually don't know. Now, if you and your friend get on the bus together, you usually sit together, right? We're going to make the assumption that you like your friend, you're sharing a seat. Orbital filling, for purposes of Hund's rule, says that everybody sits alone. Until there are no more alone seats, then everybody sits as pairs increasing. So when we think about this, we're basically going to fill all these orbitals, and we're going to learn how do we fill them, where do they go, what do they look like, and all of that as we go through the day. If you printed out the slides, super. If you didn't, your notes are going to have the following heading: Electron configuration. How do we know how to fill orbitals, and where are the orbitals? I will roughly change slides when you should move to the next heading, but there's nothing on here because I'm going to draw all over the board. So that's where we're going. That's what we're going to think about. So electron configuration. If we know that an element contains 25 electrons, such as manganese, where are those electrons? It turns out that we fill them in order, both in the order in which we encounter them in the periodic table, which I'll show you in a minute, and we think about it in terms of where they are energetically. So the other thing, if you looked at the Chapter 6 worksheet, there was a question that said to write and draw the electron configuration, which is not on today's mini exam, but it will definitely be on number 5. So if I tell you to draw the electron configuration, I would like a line with arrows on it. If I tell you to write it, it's 1s, 2, 2s2, where we have the n equals, then we have the orbital, and then this 2 is the number of electrons in an orbital. Drawing and writing, those are the 2 ways I'm going to ask you about it. We will talk about the single shortcut there is available on mini exam 5, so I know in 2 weeks, I will tell you this again tomorrow. whatever time I see you again, not tomorrow. The reality is, the question will ask you to do one of these. You can do both, but if you do the wrong one, you will get less credit. Even if it is correct, but not what I asked for. So I will always tell you, I'll give you as much details as you need at the top of the page, where it usually is. So when we think about this, the electrons fill fully the n equals 1 shell, then the n equals 2, then the n equals 3. We know that in the n equals 1 shell, the L equals 0 is the s orbital. So n equals 2 has s and p, n equals 3 has L equals 0, s, L equals 1, make that longer, and L equals 2. So these are the d orbitals, and these are the p orbitals. And so as we start to look at these, we basically fill them as we encounter them, starting from the 1 going to n equals infinity. So let's look at some relatively simple examples. So for lithium, we're going to have the 1s, the 2s, the 2p, and the 3s. 1s, 2s, 2p, and the 3s. So lithium contains 3 electrons. S orbitals can hold 2. So the first 2 go in the 1s. The third goes in the 2s. You fill them literally as you encounter them. S's get 2, P's can hold up to 6, D's can hold up to 10, F orbitals can hold 15. If you want, yeah.
15 or 14?
Ooh, did I say 15? I meant 14. You're right. Sorry. My brain is a little mushy. I think I ate way too much candy last night because I didn't have any trick-or-treaters. Which makes me sound sad and depressing, but not most. So, if you want to write it, it's 1s2, 2s1. This is the 1s, and it contains 2 electrons. The 2s only has 1 electron. So if we look at boron, it has 5 electrons. So we're going to fill the 1s, 1, 2, 3, 4, 5. This singular electron could have gone in any one of these orbitals, because they're all the same. You can put it in the middle, you can put it on the right, you can put it on the left. That's a you choice. So from here, you would write that 1s2, 2s2, 2p1. Nitrogen has 7 electrons. So there are 3 electrons in the p orbitals. Based on Hund's rule, we know that they have to fill each p orbital independently before they go into the next. So this would be written 1s2, 2s2, 2p, 3. Any questions thus far? Ow. Yeah.
So, sorry, I feel like you probably said this and I just in one ear and out the other, but for the Hunt rule, and you mentioned the bus example where you kind of did the courtesy seat, does that only apply to the d orbital?
It will apply to the p, d, and f orbital.
Not the s.
Not the s, but it does. There's just no degeneracy. So the s orbital, it's okay. The s orbital only has 1 set of seats.
Okay, so it just fills the second one immediately.
It fills the second one because there is nowhere else.
All right. Thank you.
So the same rule applies no matter what it is, but sometimes there's just it's like a weird bus. It only has 1 seat.
It's hard for me to visualize because I saw you pull the 1s and then the 2s immediately, which makes sense with your example as well, it's just because of the way it was visually on the board.
It's okay.
When you're writing the electrons in the slots, is that the particular order you want the arrows? Like the up and then the one going down? Is that the way you want it? Like what happens if we do the down first and then the up?
If you did that,
Yeah.
that would be equally fine. I That's just not how I think. It is equally fine. It is perfect. I just do it the other way. You may write them in any way you like. The only way that gets a little funky is if you do, no, where the barbs are on the inside. That, which I think is also acceptable. It just kind of makes my brain hurt. So this or this either are pretty much the same. This, I believe, is also correct, just unattractive. And that is, in my own personal opinion, I will also accept any of those methods. Other questions?
So even if it's just like one arrow, it's still going to be counted the same as if it was like 12 of them in one slot.
Say that again.
So like with nitrogen, how there's only like the first two are full, but then when you get to P, there's only still like basically just a half arrow instead of like full arrow, still kind of the same as.
So each of these lines counts as one electron. So there are 1, 2, 3, 4, 5, 6, 7 in nitrogen. But because of Hund's rule in the degeneracy, meaning these three are at the same. So the other example, fidget spinners, which maybe you've seen them, maybe you haven't. If you have, well, you probably have. Maybe you've never explored them. It has 3 equally balanced prongs, so they spin somewhat perpetually. If you were to tape a penny to one side, it will not spin the same as if you taped 3 pennies. So the reason you do 1 into each is because this is energetically more favorable because they are all even. If the alternative, which is wrong, just in case you're like not focusing here, the alternative would have been for you to do this. And this is an unbalanced situation because this orbital is fully filled and this one is fully empty. Where you could do this, which gives you a more balanced, even filling of the orbitals. Question. What questions do we have? Yeah?
So they'll face them up, do they have to face up, or would they?
You can face them down. As long as they are, these 3 have to all be the same. But if you want to go down, that's your choice. They just all have to go in the same direction. Other questions? Yeah?
Sort of curiosity question, but why do they all have to be in the same direction? I know that you're indicating to me whether or not it's the positive, like 1/2 or negative 1/2, but why does it matter?
So they all go in the same direction because when electrons spin in one direction, it generates a very small magnetic field. And when they do not all spin in the same direction, it changes the stability of that. So when you think about, there are some materials, semiconductors, nanowires, nanorods, where you can basically force them to flip, and you get some other arrangement, and it changes the distribution of the energetic states. And when you do that, some cool things happen. But the most stable state. So you could have them alternating, it's just not the most energetically stable state. So you can do lots of crazy things, not crazy, but interesting things with the electrons. And so if you were to do 2 up and 1 down, it is a slightly higher energy than all up or all down. And that higher energy can lead to destabilization if you find it in a bond. It can lead to different types of decay. The dual brings all kinds of weird things, but cool things. So that's why they do that.
So then they don't actually spin the same direction if the charge is off by that half?
But so in this example, they all spin in the same direction.
Right.
If you do it in the 2 up and 1 down, 2 would spin in one direction and the other would spin in the opposite direction.
Okay.
And it would change the magnetic properties. If they are magnetic, it would change basically the properties of how the electrons can interact.
Right.
And in chapters 8 and 9, we're going to start talking about bonds. And it'll frankly destroy the bonds. Good question. Other questions? Yes.
So for angular momentum, or I'm sorry, it's kind of abbreviated. Did I check?
I mean, is it relevant to this?
Yeah. I just want to make sure that I was understanding like how like a certain orbitals work. Like for angular momentum from number the third one, the lettering is going to be represented to like which layer it is, right? Because the S can only take it for and it is for the zero number of angular momentum.
I'm not really sure what you're asking and how it pertains to this information. So are you asking what M sub L means? Are you asking what L means?
That's what L means, yeah.
L tells you the orbital shape. So L equals 0 is an S. L is defined. There are lots of allowed values, but L equals 5 always means the same thing.
Okay.
So let's think about neon. We have 1s, 2s, and the 2p. These are all fully filled. If you ever watch me do this on a video, I talk while I do it. I basically count them out. For anything we've done this far, there aren't very many electrons, right? So it's pretty easy to look at it and be like, yep, see where we're going. So in this case, you could write this 1s2, 2s2, 2p6. So we all know where this goes. We're going to something, down here in the periodic takeoff. So let's think about potassium. So potassium has 19 electrons. And so we have the 1s, we have the 2s, the 2p, the 3s, the 3p, and the 4s. And so in this case, we are going to fill them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Math. That takes forever. You should be prepared to write the whole thing or draw the whole thing in any of these ways. But sometimes we only really want to think about the core and the valence. So the core is basically the inside. So this is the core. This is the valence electrons. So the valence is what's on the outside. It is in the largest n equals shell. So the core is in a fully filled n shell. The core definitely corresponds to a fully filled noble gas. Noble gases are the ones all the way over here on the right. So if you look at argon, we have the 1s, 2s, 2p, 3s, 3p. And it looks like this. Well, that needs to be closer because it's fun. So the argon core looks, if you write out the electron configuration, it looks like this. So it turns out that for potassium, we can use the noble gas configuration. Where the fully filled core is annotated by the previous noble gas in brackets. So this is the noble gas configuration. When we start to think about bonding, only valence electrons are important. So the core is basically the irrelevant portion. Yeah.
I think that I was going to ask you a question about exactly what you're getting to, so I think I'll just hold on to it for now.
Excellent. So in this case, we have this noble gas configuration. Now, some of us want to say like, ooh, argon, I could just write it as this. Like it's a noble gas, it's fully filled. It turns out that that is not true. So for noble gas, for argon, you would need to put neon 3s2, 3p6, because it has valence electrons. When you just put the brackets around it, we assume that it's the core. And the core and the valence shell cannot be the same. So you can write or draw any of these using noble gas configuration. In the instructions to the problem, it will say, do this using noble gas configuration, or use this, and you cannot use noble gas configuration. Questions about this such thus far? Yeah.
Can you explain that again?
Yeah. So if you look at your periodic table, we see potassium is element 19, and argon is basically up and all the way over. So the electron configuration of the first 18 electrons for potassium looks just like argon. So we can basically, instead of drawing all of this plus the 4s, you could annotate it as the argon plus anything past the argon. So every row, you get a noble gas. And so anything in the same row with potassium has the same argon noble gas core. And as you move down the periodic table, you can basically open up new noble gases at each shell down your periodic table.
So because potassium has the 4s, but argon doesn't. So argon's the one on the bracket.
Yes.
So 4s is for the potassium.
Mm-hmm. So this basically says that all of this, this is just a shorthand for that. And this is whatever else the new stuff is. It's kind of like saying, I need you to pack an outfit. I'm really only asking about your outer layers. Like, I say, what are you going to wear to this event? I'm asking, like, your shirt, whatever kind of pants you're going to wear, and shoes. I assume that everything else you're going to take care of on your own. That is the core in this situation. Other questions? So how do we know how to fill the orbitals? Thus far, I've basically said things like, you know, this is here and this is there. It's fair statements. So the reality is, the orbital filling follows two patterns. I'm going to show you the first one, and then we will start our discussion of the second that will be completed on Wednesday. So if you write it out, where every end shell, so we have n equals 1, n equals 2, it turns out that every end shell has an extra set of orbitals. Now, I didn't draw the 5G, or the 6G, or the 6H. Not all of these exist, but you will fill them when they are discovered in this manner. You're going to draw diagonal lines that you annotate 1, 2, 3, 4, 5, 6. To where you fill the 1s, then the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Now, the reason the 3D is filled before the 4S, nope, 3D is filled after, has to do with this. If you were to zoom in, which is virtually impossible because you have eyeballs, the 4s and the 3d are really, really close in energy. It turns out that the 4s is slightly below energy in the 3d. Once you fill the 3d, it falls back underneath. So the question becomes, what does all this mean in reference to our periodic table? So by now, we should be relatively familiar with how the periodic table looks. It kind of looks like this. I have moved helium, which usually lives here, over there with hydrogen. The end shells correspond to the rows in the periodic table. N equals 1, N equals 2, N equals 3, N equals 4, 5, 6, 7. So you can tell any electron in the main body where it is, kind of based on the row. It turns out that the first two columns are the s orbitals. Over here are the p orbitals. Here in the center, we have the d orbitals. And these are the f orbitals. The hardest part of this filling is you basically fill them as you go across. Except, we know, based on the quantum numbers, that there are d electrons in the n equals 3 shell. It turns out that this is the 4, and these are the 3d, and these are the 4p electrons. So you have to remember, using this method, that the d orbitals are offset from the s and p orbitals. Questions? This is not the end of this discussion.
It's sort of tying in what we're learning now from an earlier lesson. You mentioned like way forever ago when we first talked about ions and bonding that they would always want to, they're at a certain place in the table, they're going to have +1 or +2 or whatever.
Yeah.
And what I'm getting at essentially now is, for example, the argon notation you showed us in potassium, that leaves one valence electron. I'm assuming that's the positive one ion that we're looking at. That's why it's the part of the thing. So to just give it that one extra into our case.
Yes, and we will talk about that in chapter 8, which should be sometime next week. No, maybe next. We're going to get there, but you're on the right track. That is definitely correct. It has to do with the valence electron. Yeah.
So the line going through all the modes, that's corresponding to the edge on the periodic table, right?
These?
Yes.
These are the order in which you go. Like you fill 1, and then you do 2, then you do 3, then you do 4.
All right.